Hi everybody, my name is Maxime Chevalier-Boisvert and I'm a grad student at the Universite de Montreal, and I do research in dynamic programming languages and more specifically dynamic programming language optimization. And today in this talk I'm going to give you a little bit of the history of dynamic programming languages with an angle towards optimization, what's been done to make them run fast. So Donald Knuth recently said, "I think of a programming language as a tool to convert a programmer's mental images into precise operations that a machine can perform. The main idea is to match the user's intuition as well as possible." And this last part resonated with me. I think that dynamic programming languages have recently acquired a lot of popularity, and the key to understanding that is that they match the user's intuition better. They allow you to express your ideas at a higher level and to leave more things implicit and have the machine accomplish those things more directly. So in terms of programming, I think to understand dynamic languages, we have to go back to the beginning. So the first digital computer, the ENIAC, had to be programmed by flipping a large number of switches on a panel, but it also wasn't a truly general purpose computer. It had to be rewired for each program that you were going to run on this machine. And so this was extremely time consuming and error prone. And people quickly looked for ways to make the programming of computers simpler. And one of the first innovations they came up with was to apply the idea of punch cards to programming. So this is a 1620 IBM assembler punch card, where you punch holes in the card to directly represent machine instructions that the computer is going to run. And so this allows you to program your program once and then to be able to run it many times. Of course, programming punch cards is very tedious. If you want to debug them, you have to look through all of your punch cards. It's easy to get them out of order. And here we have a stack of punch cards where somebody labeled the functions, the subroutines on top. And of course, punch cards being paper have to go through a punch card reader, which is a mechanical device, and they were also prone to jamming, so destroying your punch cards. And so people, again, looked for ways to streamline the programming process and make it easier. And this is a quote by John Backus. "Much of my work has come from being lazy. I didn't like writing programs, and so when I was working on IBM 701, writing programs for computing missile trajectories, I started to work on a programming system to make it easier to write programs. And this programming system was going to be Fortran, which stood for Formula Translating System. And from the very beginning, it was geared towards engineering and military applications. But now you had the possibility of writing your program in a text format and editing them on a terminal and then compiling them and letting the computer do that work for you. At the same time as people were working on Fortran, John McCarty was beginning his research into AI at MIT. And he had a mathematical background. He had a PhD in mathematics. And so he wanted to have something more symbolic. His research was going to be about common sense reasoning and automated theorem proving. So he wanted a language where you could operate at the level of recursive symbolic expressions. And this was going to become Lisp. I think also that one of the main driving factors was platform independence. He wanted portability, and this was especially important at the time because nowadays, we still think of portability as something really important. But in the 50s, they hadn't even agreed on the 8-bit byte. For example, the computer that the original Lisp was written for, the IBM 704, had 36-bit words. So in 1960, he published this report, Recursive Functions of Symbolic Expressions and Their Computation by Machine, Part 1. There was never a Part 2. And this outlines the original Lisp and many of its important features. I would say that Lisp had a lot of influence on the languages that followed it. It was the first dynamic language and also the first functional language. And many of its features are still found in all dynamic languages today. Features like dynamic typing. So types are associated with values and not with variables, as in static languages. late binding, so names are resolved dynamically. When you call a function, the lookup is semantically done at runtime instead of statically resolved. The eval function, so this idea that you can generate new code and evaluate it dynamically. And finally, the read eval print loop, which was enabled by the eval function. So the idea that you can write code and test it interactively. And this must have been revolutionary in the late 50s and early 60s, because people were still at the time programming by punching cards. So this idea that you could be in front of a computer and write code and immediately get a result must have been really game-changing. And finally, there's also garbage collection. Lisp is a language that generates intermediate data that operates on list. And so without garbage collection, Lisp would have been pretty much impossible, because you would have had to constantly be freeing up all the closures that you allocate and all the intermediate lists. And so garbage collection was invented for this original Lisp. Now, unfortunately, dynamic languages have this reputation for being slow, or at least slower than statically typed programming languages. And we should probably ask the question, why? Well, it's because a lot of the features that make it so convenient to use also introduce some overhead. And especially at the time, they didn't really know yet how to make those things fast. So garbage collection was invented for Lisp. So it was really in its infancy at the time. And they used a mark sweep garbage collector, which was fairly inefficient because you needed to traverse all of the objects that were allocated in order to find out which ones were still live. Also, stop the world GCs, garbage collectors that can introduce a pause when they interrupt your program to do garbage collection. And there were also semi-spaced GCs, copying garbage collectors, that were invented shortly after. But these can cause a huge waste of memory, because you're actually having to reserve half of your heap to be empty space for the next collection. And at the same time, you actually waste even more memory than that, because if your half heap, your semi-space is near full, you're going to be garbage collecting all the time. So you actually need more like 4 to 7x overhead. And then there's dynamic type tests. So operators in dynamic languages change meaning depending on what values you're passing to them. So they perform a different operation based on the input types. So for example, the plus operator in a language like JavaScript could mean integer addition. It could also mean floating point addition. It could mean string concatenation. And in some other languages, it could also mean array concatenation. So inside each operator, you have many different operations and many hidden type tests that have to be performed dynamically. So this is an example from JavaScript. If you have a simple function that just does n+1, if you do add one of 2, it's going to return the integer 3. If you do add one of hello, it's going to do string concatenation. If you do add one of true, you get 2. If you do add one of null, you get 1. Add one of undefined, you get not a number. Add one of an object with a toString function that returns the string 3, you get 31. But toString doesn't actually have to return a string. It could also return an integer, and then you get 4. So inside of the JavaScript plus operator, you have to be able to handle all of these cases. Yes. And then there's property access. In a language like JavaScript, objects can grow dynamically, and properties can also be dynamically deleted. And then you can do property enumeration. You have some introspection capability. So objects in JavaScript and similar languages behave a little bit like hash maps, where you're mapping string keys to values. But hash maps are relatively inefficient. They're big O of 1 in terms of access time, but the constant is large. And they also require you to store key value pairs, but you don't want to store keys and values for all the properties inside of an object. You only want to store the values, ideally. And then finally, there's the eval function that comes and complicates things. So dynamic languages are not untyped. They have typing rules. So for example, if I had the plus operator and I say C equals A plus B, I could say that adding an integer to an integer produces an integer, adding a string to a string produces a string, adding string to integer produces a string, and so on. So ideally, I'd like to have a smart compiler that can do some amount of type inference and eliminates unnecessary type tests and make my program run faster. But eval complicates things because it allows you to evaluate arbitrary code at any point. So with eval, you could potentially be redefining any function any global variables, sometimes local variables. You could be introducing new code into your program, and this really complicates type inference. So one of the earliest strategies that was found to optimize dynamic languages was called type tagging. And so this is basically a heuristic compromise. We're saying we're going to prioritize common operations like integer and list operations. We're going to assume that most of the operations that we do in a language are going to be on integers and lists. And so, for example, if we have 32-bit words, we're going to steal the lowest 2 bits to be a type tag. So for example, 00 would mean that my value is an integer, 01 could mean pair, and 11 would mean pointer. And then what happens is that we avoid having an extra level of indirection when we're fetching an integer or a pair. And so we get better performance for these operations. We get faster type tests. We get less allocations. We don't have to allocate temporary memory for integers where there are no integer objects. And so we also do less memory accesses. But this is a compromise because it also adds a little bit of overhead to box and on-box values inside of this type-tagged representation. Now, the 1970s were dominated by mini computers like the PDP-11. So most of the computing in universities was done on machines like this. And these machines were relatively slow compared to modern machines. They sometimes run at speeds that were less than a megahertz and had memories that were counted in kilobytes, up to maybe a few hundred kilobytes. And they were sometimes shared between many users. And in a sense, maybe it's not so surprising that Lisp didn't become a dominant programming language at the time because the resources were so limited and people didn't yet know how to make dynamic languages fast. And so they would go to static languages to try to get better performance, better memory characteristics, and so on. But fortunately, people didn't just give up on dynamic languages. This machine here is the Xerox Alto, designed at Xerox PARC. So Xerox had a lot of success with copiers, but they wanted to diversify. And they tasked their employees with inventing the office of the future, the paperless office. And this was going to happen with computers. And so they had this big program where they designed these machines internally, and they had their employees use them. And these machines were really revolutionary. They were all networked with each other. They had files and print servers. They had a mouse. And this was happening in 1972, by the way. They also had bitmapped graphics and graphical user interfaces with desktop metaphor that we're all familiar with. And to program these machines, the Smalltalk language was invented. And Smalltalk is probably one of the most influential dynamic languages out there. It sort of influenced languages like JavaScript and Ruby and Python and so on. It was object-oriented. It had classes and objects, and also the possibility of dynamically growing your objects and so on. And it also had this concept of a live image where everything lived inside of the same Smalltalk system. So you could be programming, and your editor, which you were editing your Smalltalk code, was itself written in Smalltalk. So you could modify your editor inside of the Smalltalk system while you were programming in Smalltalk and so on. And you also had a system browser where you could browse all the classes in the system and modify the kernel. You could really shoot yourself in the foot if you wanted, but it was also extremely powerful and dynamic. And at the same time, you could suspend at any time your Smalltalk image to a disk. So you can interrupt your session and save it to a disk like this, which could be carried between different workstations. So what did Smalltalk do about the efficiency problem? Well, because the entire machine was designed by people inside of Xerox, they sort of had access to every layer of the design. And so they were able to implement special micro-coded instructions that were geared to the Smalltalk VM implementation. So they optimized Smalltalk also by conceiving specialized instructions for the CPU. And at the same time as this Smalltalk research was going on, Thomas Knight and Richard Greenblatt at MIT were working on the Lisp machine. And the Lisp machine had one of its major goals was to make Lisp fast. So they wanted to tailor the hardware to the execution of Lisp. And they did this by having a tagged architecture where each word of memory had extra tag bits of metadata for type tags and also for CDR coding, for compressing list representations. And the CPU was directly aware of those type tags. So they had specialized instructions where the fast path and the type test could be executed simultaneously. So instead of having operations where you need to first test the type of value and then perform an operation, they could do things like have an add operator that would do floating point addition and integer addition and type tests all at the same time and then select the right answer based on the type test. They could also do array bound checks in parallel with array access to save time. And they also use micro-coded instructions to implement some Lisp primitives basically directly inside the CPU and to reduce call overhead sometimes to as little as 20 cycles and to optimize garbage collection. Interestingly, the operating system was also written in Lisp. And so there were many spin-off companies that were created by MIT students that really fell in love with those Lisp machines. For example, this is the Symbolics 3600 series Lisp machines. Now, unfortunately, the Lisp machine didn't really survive, and I think one of the things that killed it is the arrival of the microprocessor and eventually of the personal computer. And maybe you could say that this is a bit of the rise of worse is better in a sense. PCs were not nearly as fast as workstations like the Lisp machine and the Xerox Alto, but they cost less than $1,000, whereas Lisp machines cost as much as $10,000 to $50,000. And they couldn't be mass produced. They were done with techniques like wire wrapping and discrete logic. So the logic inside the machine was very much handmade by a lot of employees, whereas PCs could be mass produced in factories. Another thing that contributed to the death of specialized hardware and the Lisp machine is that people found better ways eventually to make dynamic languages faster. For example, Neil D. Jones invented a flow analysis for Scheme, which was able to deduce types based on typing rules for the language and eliminate type checks and dynamic lookups. This particular technique doesn't really solve the problem of eval, but in Scheme they had this advantage that eval had more restricted semantics, so you could pass it an environment to execute in, and it couldn't touch the local variables inside of your functions. And so this analysis, KCFA, is very useful for Scheme, but a little less applicable to other languages. There was also more research done at Xerox PARC. The self-programming language was basically a descendant of Smalltalk. And I saw it described on Hacker News as a small talk that was more Smalltalky than Smalltalk. So it was even more dynamic. Basically, everything was an object. Even your stack frames, your local variables inside of a function were accessed through an object. But despite the fact that it was even more dynamic than Smalltalk, they found ways to make it even faster. So they claimed up to half the speed of optimized C. And this was due to several key innovations like type feedback and profile-driven optimization. So this idea that you can let your program run for a while and observe the types that actually occur in your program and then generate better code based on the types that you observed. They also had inline caching to speed up property accesses, inlining of message sends, and dynamic de-optimization. And finally, maps, which are really crucial for dynamic languages to optimize object layouts. So what is the idea of maps? Well, in JavaScript, you can create object literals like this. And ideally, you would want to represent them as classes, but the objects behave a little bit more like hash maps. So ideally, you would want to have a class layout for your object literals, where you say, I know exactly the offset in memory of each property. So X would be like at offset 0. And then in my object literal B, I could say that A is at offset 0, B is at 8, C is at 16, and so on. So basically, you would like to be able to access your objects as if they were C structs and you knew exactly where each member is located. But this is a bit problematic because in most dynamic languages, you can add properties dynamically, which would invalidate any fixed layout that you come up with. And you can also delete properties dynamically. So what can we do then? Well, the idea behind maps is that you can actually have multiple class layouts for your objects. And so your objects can change class dynamically at execution time. So you can have multiple fixed class layouts and have the objects change the class they belong to. So this is like the idea of hidden classes that's used inside of Google Chrome. During the 1990s, we saw the rise of many dynamic languages. Most of them interpreted, most of them not very fast, but I think we got to the point where PCs were so fast that it didn't matter so much anymore. And also maybe in the web world, people cared more about fast prototyping than they cared about having absolute execution speed. But there were nevertheless projects to optimize some of these languages, projects such as PyPy and lier, which focused on tracing and managed to get some very good results in terms of performance. More recently, there's been a war between Mozilla and Google for the JavaScript performance crown, and this has been a big driving factor in improving the performance of dynamic languages. So Chrome has a fast baseline JIT internally. So they have a JIT that can generate code that is not very optimized, but that generates code very fast to allow it to start executing your program very fast. And they also have the crankshaft optimizing just-in-time compiler to generate more optimized code. And internally, they use a lot of the techniques that were pioneered for languages like Self. So they have hidden classes that are a bit like maps for object layout, and they use inline caching, type feedback, dynamic de-optimization, which allows them to undo inlining decisions if they find out that those inlining decisions are wrong, and on-stack replacement, which allows them to replace functions by optimized versions at runtime. Inside of Firefox, there's an interpreter, a baseline JIT, and the iMonkey optimizing JIT. So you have a bit of a similar structure where the interpreter allows them to start executing your program very fast. What they do is they do a lazy first parsing. So you can dump a lot of JavaScript code on it, but the first parsing will actually only check for syntax error and establish where the functions are located inside the file. And then only the first time that you call a function will it generate bytecode and parse the function. And then they use a lot of the same techniques that were pioneered for Self, like maps, inline caches, type feedback, dynamic de-optimization, and so on. But recently they've made an innovation, and they added an extra ingredient, which is a hybrid type inference analysis. And the reason why this is significant is that they finally found a way to solve the eval problem. So they will be able to incrementally analyze your program, essentially, and get some type inference results that are correct up to the current point in execution. And then if you do an eval and you introduce some new code that invalidates some of their optimization results, they will be able to analyze that new code and reanalyze the rest of the program and update the types that they've inferred with their analysis, and essentially recompile the parts of the code that are no longer valid dynamically. And this makes a tremendous difference on benchmarks, has allowed them to beat Chrome on some of them. So where do I come in? Well, I've done my master's thesis at McGill University, and my advisor wanted me to work on optimizing the MATLAB programming language. And I think she was very interested in numerical optimization, so optimizing matrix multiplications, for example. But what I latched on was the fact that MATLAB was a dynamic language, and that it would be very useful, for example, to be able to do things like type inference and infer the dimensions of matrices and so on. And you need type information to be able to optimize this code. I also came to believe that dynamic languages require dynamic compilers. That is to say, to successfully optimize dynamic languages, we need to be able to have a system that can react at runtime to the changing state of the programs. And what I'm working on right now is a JavaScript VM called Higgs. So Higgs has an interpreter and a JIT compiler for x86-64, and has support for most of ECMAScript 5. So it's a JavaScript VM. And it's a platform to try various optimization ideas. It's got a relatively small code base, so less than 50,000 lines of code, which makes it easy for one person to understand the whole thing and for me to refactor as much of it as I need. And what I'm working on right now is an optimization technique called basic block versioning. So this has some similarities with techniques like tracing and procedure cloning. So the fundamental idea is that as you compile code, you can accumulate information, accumulate facts that help you to optimize and specialize this code, and compile multiple versions of the code that can handle different types efficiently. So some of the information we can specialize based on is things like low-level type information, register allocation state, and also object types and global variable types. So how does this work? Well, a very simple example here. Suppose we have a loop that does a lot of bitwise AND. So each iteration, it will compute the bitwise AND of v and I, and also increment the loop counter I. So this is actually from the SunSpider bitwise AND benchmark. So to a compiler, this loop will look a little bit more like this. That is, each operator is actually sort of like a function that has some complex logic hidden inside. So the less than function, the less than operator is a function call, and so is the add, and so is the bitwise AND. And inside an operator like bitwise AND, typically what's going to be done is that we're going to check the type of the inputs x and y, and then we'll have a fast path here that will use an optimized machine instruction that does bitwise AND only in integers. And if x and y are not integers, we're going to have a slow path where we sort of do the general purpose operation. So we're going to convert x and y to integers and then do a bitwise AND on that. Same thing goes for the add operation. Typically, we'll do a type test and we'll have a fast path. And then if x and y are not actually integers, we're going to handle the case for strings and all the other types elsewhere. There's an extra complication in that add will have to do an overflow check. It'll have to check that the result of the add actually fits in a 32-bit integer. And if it doesn't, it will have to convert x and y to double values and do the operation on a double instead. And similarly for less than, we're also going to have a fast and a slow path. And so putting it all together, the loop is going to be transformed into something a little more like this. So each operator is going to have a fast path and a slow path. So now this introduces a bunch of type tests into our loop. And to make our program run fast, we'd like to eliminate them. So the first thing that's pretty obvious is that testing the type of a constant is not necessary. So we know that those values, 600,000 and 1, are integers. So we can immediately eliminate those type tests. So this leaves us with the following. So how do we eliminate those? Well, with basic block versioning, I'm going to make the assumption that when I enter the loop, I is an int32 value. So I know this from here. And so I can eliminate this first type test because I know that when I enter the loop, I is going to be integer. And then the same thing goes for v. It's also integer when I enter the loop, so I can eliminate those two type tests as well. And also the last one. And so I'm going to be left with only this code here. And what I see is that when I perform the bitwise AND here on those two integer values, I will also get an integer as output. And when I do the add of I plus 1, I also get an integer here. So the next time I'm going to go around the loop, I'm going to have integer values going in as well. Unfortunately, this is maybe a little further complicated by the overflow. So if I wasn't in a case where I get an integer overflow, I would be converting my values to my value I to a double and getting a double result back. So this is a bit of a problem because I've assumed here that those values were integer when I enter the loop. So what I can do with basic block versioning is say that if I get a double result, I'm going to generate a new loop version that assumes instead that I is a double. And I'm going to jump to that loop version that handles that case separately. So I can keep this loop here optimized and have another version elsewhere that's going to handle other type combinations. So this is a bit of a multi-world approach. So in a traditional type analysis, I'm going to do what's called a fixed point on types, which means that at any program point, I must have a solution that agrees with all the inputs. And so I must get a pessimistic or conservative answer. So if I don't know that a value I is integer and I have that it must be integer or float or integer or double, then maybe I have to compromise and say I don't know what the type is. But with basic block versioning, I can say I can have multiple solutions possible, and I can have multiple versions of code that handle different combinations of types. So we don't necessarily have to sacrifice performance. So basically, this is shifting the fixed point to the versioning of code blocks instead of doing a fixed point on the types. So there's a lot of interesting research questions about this, like how much code blow up we can expect, and what kind of performance gains, and what's the effective compilation time. So we've already implemented a simple version of basic block versioning inside of Higgs, and I can say that the answers to this so far are pretty encouraging. There isn't much code blow up. It doesn't slow compilation time by a lot, and it does reduce the number of type tests significantly. So for the last part of this presentation, I'd like to speculate a little bit about the future of dynamic languages, that is. So speculating about the future is maybe a little risky. People have been notoriously wrong. But I think that if we look at the past and the present and current trends, and maybe we extrapolate those trends only a little bit into the future, we can probably make some good educated guesses. So what does the future hold? Well, I think there's at least 3 things that are going to change in terms of dynamic language optimizations, 3 aspects. I think we're going to get more advanced, smarter CPUs. So this is probably pretty obvious, but like CPUs like the Intel i7 are very, very advanced now. They do register rewriting behind the scenes. They had huge multi-level caches. They have the ability to dispatch and execute multiple instructions per clock cycle. They do branch prediction. They do a lot of things behind the scenes that you don't see. I think that probably Intel is going to throw even more silicon at the problem, and maybe we're going to see CPUs that can actually execute multiple branches in parallel speculatively, for example. We're also going to get more instructions per cycle and so on. And it's going to get to the point where, despite the fact that we don't have hardware that's specialized for dynamic languages, we're going to get sort of the same results. Maybe eventually we'll be able to run our type tests and our typed operations simultaneously inside of the CPU. I also happen to know that Intel is speaking with people at Mozilla about new instructions that will be specifically made for optimizing dynamic languages. So those might come in the next few years. I think we're also going to get smarter compilers. So people don't like hearing about sufficiently smart compilers, but compilers are in fact getting smarter. There are new techniques that are being devised for optimizing dynamic languages. And there's also a lot of techniques that have been invented in academia that are not in use just yet, that haven't really made it, but that will probably make it into modern dynamic language compilers in the next few years. So we're going to get better optimizations. And also maybe better language design. So what do I mean by better language design? Well, I think it's important to remember that JavaScript is a language that was designed in all of 2 weeks by Brendan Eich when he was working at Netscape. So when he designed JavaScript, he didn't really have performance in mind. He wanted to have a language to write glue code to fit on top of HTML. And so many of the features of JavaScript make me, as a compiler writer, want to pull my hair out. But if we had dynamic languages that were designed more with performance in mind, maybe we could actually do a better job at optimizing them. And finally, in terms of the future of dynamic languages, I think that there's a number of good ideas coming from other languages that have caught on. So from Lisp, for example, we got dynamic typing. We have closures now. If your language doesn't have closures, people don't take it seriously. It's become, everybody's become convinced that closures and the REPL, for example, are good features to have. From the Haskell and ML world, we're starting to see type inference make it into dynamic languages, except that type inference in dynamic languages is going to be transparent. It's going to be happening behind the scenes. From Smalltalk, we're seeing that prototypal inheritance and duck typing has become relatively mainstream in JavaScript, for example. I think that there are more good ideas from those languages that maybe will eventually become mainstream. So from Lisp, the ideas of macros and domain-specific languages will maybe become eventually mainstream. Maybe also the idea of AST manipulation, so code is data. In Lisp, you could actually generate ASTs directly. You can't really do that in modern languages, but maybe we'll get languages eventually that can look at their own AST and modify them and implement a macro system in function of that. I also think that ideas like pattern matching and non-nullable types from Haskell will eventually propagate because they're actually really good ideas. And maybe also a focus on constantness, purity, and immutability. This is becoming increasingly important with multi-core and distributed programming. And finally, from Smalltalk and Self, the idea of live programming, the idea that you can perform microsurgery on a running system. Maybe it's going to become more relevant now that we have so many distributed systems and that uptime is so critical. Maybe in the future we won't have systems that we interrupt and restart all the time, but instead we'll have systems that just run forever. And also with the arrival of non-volatile RAM, maybe having persistent systems is going to become more mainstream. So this is it for my presentation. Thank you.